Hello all, welcome to Geotechnical Engineering Laboratory. So this is the third week of this course. I hope you have watched the videos of the course. The videos were linked with permeability and the shear strength of the soil, how to find that in the laboratory. Permeability and shear strength. Shear strength consists of direct shear test and the triaxial test. So we will uh, in this video, I will share some numerical examples which will make you understand the test and also the theory in them. Let me introduce myself. My name is Muhim Majid. I am a research scholar in Civil Engineering Department at IIT Kharagpur. So let's start with the questions. Okay. So the first question is related with based on the permeability test. As we know, the permeability test. It consists of two types. One is called as constant head permeability test, and another is called as variable head permeability test. So the question number one here, it is based on okay. So question number one is based on constant head permeability test, right? So let me read the question first. For a constant head permeameter test, the following observations were taken. Distance between piezometric tappings is equal to 150 mm. Water level difference in piezometer is equal to 50 mm. Diameter of the test sample is equal to 100 mm. Water quantity 350 ml. Duration of the test 300 seconds. Find the coefficient of permeability of the soil. We have to find the K, that is the coefficient of permeability of the soil. So how to find that? Based upon the test, we have different equations here. So let me first explain a few let me explain in this constant head permeameter test. So the constant head permeability test, the head is kept constant. Okay, as you can see in this figure, this is the sample, this is the porous disc, upward and downward, this is the tank. So here the head remains the constant, that is this head remains constant. Okay, so what happens here is this water moves down through the sample, and this water is collected here. The quantity of water that is collected given by the time that gives the discharge. From the discharge we can find the coefficient of permeability using the Darcy's equation. Okay, so constant head permeability test, the equation will be K is equal to QL by AH. Okay, now we will say how can we get this equation. So it is simply the Darcy's law, that is Q is equal to KIA. We can this I is equal to H by L. From we can move this here and we can get K here. Okay, that will be like this. K is equal to QL by AH. Okay, K is equal to QL by AH. So the various terms here are Q. Q is the discharge, L is the length of the sample, A is the area of cross section, H is the head difference. Okay, Q we can find in the figure. We can find here the Q, the water that is moving out. We can collect that, measure how much it is, and divide by the time, we can get Q. Okay, L, length of the sample is, this is the length of the sample. Okay, length of the sample will be between these two, between the tappings, this tapping and this tapping, the soil here, this is the L. Okay, because we are considering this only this part, it is not the whole here. Okay, please note that it is the distance between the tappings, because in this location, in these two locations, we are finding the permeability. So I'll have explained what it is. A is the area of cross section. Area of cross section means this area, okay, internal area of cross section. H is the head difference. So this is the head difference, that the piezometer tappings here, the water level will be in this tapping here, the water level will be here. This tapping will be, the water level will be lower because the water is moving and there is head loss, so it will be lower. So this difference will be H, that is called as head difference. Okay, so let's first calculate Q. Q is the discharge. We know 350 ml we have collected divided by 300 seconds, that will give 1.166 ml per second. Please note here, sometimes you get confused. ml is equal to cc or centimeter cube. Okay, L is given as 15 centimeter. We can find the area of the cross section of the sample, that is pi by 4 d square. D is given as 10 and it comes out to be like 78.5 centimeter square. H is 5 centimeter, it is given. So Q is equal to K is equal to QL by AH. Q is 1.166, L is 15 centimeter, A is 78.5 centimeter square, H is 5 centimeter. So calculating that, we can get K as 0.044 centimeter per second. Note that we have kept all the units here in centimeter and in seconds. This is also centimeter, 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 and centimeter. This centimeter square and centimeter. Okay. So we have we are done with the constant head permeability test. Okay. Now the second question that we have, this is falling head permeability test. This question is based on this falling head or the varying head permeability test. Let me read the question first. In a falling head permeability test, the following readings were taken. Diameter of soil sample is equal to 4 centimeter. Length of soil sample is equal to 18 centimeter. Head falls from 1 meter to 0.4 meter in 20 minutes. Cross section of area of the standpipe is equal to 1 centimeter square. Okay. We have to find the permeability of the soil, that is K of the soil. So let me first make a point here. There are two types of tests, as I already said. One is constant head permeability test and another is falling head permeability test. So when to use what type of test? Okay, the constant head permeability test, it is used for the soils which have high permeability, that is means sand. Constant head permeability test can be used, which means the soils which have K value higher, the constant head permeability test can be used. And falling head permeability test is used for clays or fine grained soils. Okay, the soils which have a very much less quotient of permeability. Okay, let's go back to the question. So the figure here is the general overview of the constant head of the falling head permeability test. Here the sample, we have the sample here. This is the constant discharge. Discharge. Okay, here the water moves out. This is the standpipe. This is the main thing here. The standpipe. We have a standpipe. We don't have that constant head here. We have the standpipe. Here the water, what happens is water level decreases as it's moving. Water is moving through the sample. It moves out here. So what happens is the level decreases. We have to measure how much this level gets decreases in how much time. That gives the permeability. Okay. So for falling head permeability test, K is equal to AL by AD log H1 by H2. I request you to please go through the books and see how we are getting this equation. Okay, this is also based on Darcy's equation. We had to do some integration here and differentiation calculus things, and then we can get this. Okay, we can get this equation from the Darcy's law. Okay, let me explain the various things here. The various things are A. A is the area of cross section of the standpipe. This standpipe that we have, this standpipe, the area of cross section of this, that is A. L is the length of the sample. Here the length of the sample is whole from this to this. A is the area of cross section of the sample. Okay. H1 and H2 are the heads that are noted in laboratory. These this is the standpipe. This is a first head, and it goes on decreasing. Then it comes here. Okay, that is called as heads. T is the time taken to move from H1 to H2. Time taken to move from this point to this point. That is also calculated. That is also noted rather. Okay. Here the A is 1 centimeter square, that is given. L is 18 centimeter. A is pi by 4 d square. We are given the diameter. We can find the area, that comes out to be 12.56 centimeter square. T is given as 20 minutes, that we can convert into seconds by multiplying with 60. We can get 1200 seconds. K is equal to AL by 80 log H1 by H2. Note that the log here is in the logarithmic. It is logarithmic log, not log 10. Okay, this is Napier's constant. Okay, this is not log 10, this is log E. So K is equal to 1 into 18 divided by 12.56 into 1200 into log E 1 divided by 0.4. So it becomes 0.001194 into 0.916. It comes out to be 0.00109 centimeter per second. We can calculate, we can present it in a different way like this: 1.09 into 10 raised to minus 3 centimeter per second. Okay, so K was this for constant head for a variable head permeability test. Okay, so this is the second. This was the second question. Let's move on to another question. Okay, this third question is also based on the permeability of the soil. Calculate coefficient of permeability, discharge velocity, seepage velocity during the test with the following data. Internal diameter of permeameter is equal to 7.5 centimeter. Head loss over the sample length of 18 centimeter is equal to 24.7 centimeter. Quantity of water collected in 60 seconds is equal to 626 ml. Also, the porosity of the soil sample is given as 44%. So please read this question carefully and see what we are given and what we have to find. We are given the internal diameter, we are given the length of the sample, we are given the head loss. Also, we are given the quantity of the water collected and the time taken to collect that much of water. Porosity of the sample is also given. We have to find the coefficient of permeability, discharge. So here velocity are of two types here: discharge velocity and seepage velocity. I will explain the difference between them in the question. Okay. So let's first calculate the hydraulic gradient. What is hydraulic gradient? It is loss of head per unit length. That is, it is denoted by I. It is equal to H by L. H is loss of head per unit length. That means how much loss is taking, how much loss of head is taking when the water moves from this to this position. Okay, that is called as hydraulic gradient. It is H is given 24.7 centimeter, that is loss of head, and L is given as 18 centimeters. So hydraulic gradient comes out 1.37. Porosity is given as 44%, that means 0.44. So we know that according to Darcy's law, V is equal to Ki, or we can say in terms of discharge, Q is equal to Kia. Why is that? Because V Q is equal to V A into V. Okay, that's why. So Q is equal to Kia. Q we can calculate from the discharge how much we have in how much seconds. 626 ml were calculated in 60 seconds. So that means the discharge is 10.43 ml per second. That is equal to K into I. We have calculated A is equal to pi by 4 d square. 7.5 centimeter is the diameter. So working out that, we can get K is equal to 0.172 centimeter per second. Okay, so we found the coefficient of permeability. So here V is equal to Ki. We know that from the Darcy's equation. K we have calculated, I we know, so we can get V. So what V is here? It is the discharge velocity or the superficial velocity. Okay, there's a difference between two. This is called a discharge. This is the discharge velocity or superficial velocity. What does that mean? That means we have the soil sample here like this. It consists of soil particles and the air voids. So water is moving through the air voids, right? It cannot move through the solid itself. Okay, it is moving through the voids. So in this superficial velocity or discharge velocity, we are considering whole of this area to calculate the velocity. V is equal to Q by A. We are considering A here is the whole of this area. That is called A is whole of this area, which gives the superficial velocity or discharge velocity, right? For seepage velocity, another thing is seepage velocity. It is defined as Vs. That is equal to Q by A. Okay, here A is the area of the voids. Here, suppose this is cross section. The area of the voids that we have, air voids, it will be less. Obviously, it will be less. When this will be less, V will be more. Vs will be more. Okay, that's why seepage velocity is always greater than the discharge velocity. So in the question, seepage velocity we can calculate by Vs is equal to V by N. This is the relation here. That means Vs seepage velocity is equal to V by N. V is the superficial velocity, N is the porosity. We have calculated V superficial velocity. Porosity is given 0.44. It comes out 0.536 centimeter per second. Okay, you can see from here Vs is 0.236, V is 0.236, Vs is 0.536. Okay, which means it's higher. This was another question based on this permeability. Now we have another small question here, question number 4. It says, in the above question, find the coefficient of permeability. We know what coefficient of permeability is. We have to find here the coefficient of percolation. That is denoted by Kp. Coefficient of percolation we can calculate by the simple formula, that is Kp is equal to K by N. K is coefficient of permeability, N is porosity. Okay. Kp is given 0.172, N is 0.44. So Kp becomes 0.39 centimeter per second, right? So the relation here is we know Vs is equal to V by N. Okay, well, Vs superficial seepage velocity is equal to superficial velocity divided by N, which means V is equal to Ki according to Darcy's law. Okay, so here what represents is K by N is represented by Kp, which gives seepage velocity is equal to Kp into I. Another relation here, please note it down. Okay. So up to this, the permeability, the numericals based on permeability are done. We have gone through the what is permeability in the previous lecture. I told the permeability, what Darcy's law is, what is permeability, and today we did the numerical on constant head and the permeability and the falling head test, and also uh, numerical on simple Darcy's equation. Let's move on to another question. So the following questions will be based on the shear strength of the soil. As we know that there are various tests that are used to find the shear strength of the soil. One is a direct shear test and another is a triaxial test. Okay, triaxial test, we have different types of tests there. One is consolidated drained test, consolidated undrained test, unconsolidated undrained test. Okay, we have another test that is called as that is used to find the shear strength of clays and very soft clays, that is called as which is called as a vein shear test. Okay, we have another test that is the unconfined unconsolidated test. Okay, these are different tests, and I'm sure you have you have watched the videos and know how these tests are performed. So we will be doing numericals in that portion. Okay, let me read the question number 5. Determine the shear strength in terms of effective stress on a plane where total normal stress is equal to 200 kilonewton per meter square, pore water pressure is equal to 80 kilonewton per meter square, C dash is equal to 16 kilonewton per meter square, phi dash is equal to 30 degrees. Okay, here we have to find the shear strength of the soil in terms of effective stress. In terms of effective stress, stresses are two types: total stress and effective stress. We have to find it in terms of effective stress. Normal stress is given and pore water pressure is given. C and phi is also given. We have to find the shear strength. So sigma is equal to 200 kilonewton per meter square. Pore water pressure is equal to 80 kilonewton per meter square. This is the total stress. We know that effective stress is equal to total stress minus pore water pressure. That is 200 minus 80. It is 120 kilonewton per meter square. From the Mohr-Coulomb equation, we have shear strength is equal to C plus sigma tan phi. In terms of effective stress, it is equal to C dash plus sigma dash tan phi dash. Okay. Tau f is equal to 15. It is given, C is given as 15 plus sigma dash, we have calculated 120. Tan phi, tan of 30. Phi is given as 30. So working out this, we can find the tau f that comes out to be 84 kilonewton per meter square. Okay. Let me move on to another question. Question number 6. A dry cohesionless soil was tested in a triaxial machine. The angle of shearing resistance is equal to 30 degree and the confining pressure 200 kilonewton per meter square. Determine the deviator stress at which sample is failing. Okay. Read the question carefully. What we are given? We are given cohesionless soil. Okay. We are given it is a triaxial test. Shearing angle of friction is equal to 30 degree, or angle of shearing resistance is equal to 30 degree. Confining pressure is given as 200 kilonewton per meter square. We have to find the deviator stress. Okay. I believe you know what deviator stress is. I will still explain. Deviator stress is basically sigma 1 minus sigma 3. Sigma 1 is here the major principal stress, sigma 3 is the minor principal stress, or we can say it is the confining stress. What difference between them gives the deviator stress, right? So in the question, cohesionless soil is given, which means C is 0, right? Cohesionless soil, it doesn't have any C. Here the equation that we'll be using is this. Sin phi is equal to sigma 1 minus sigma 3 by 2 divided by sigma 1 plus sigma 3 by 2. Sigma 1 is major principal stress, sigma 3 is minor principal stress. So if you want how this equation is coming, I will explain how this is coming. So we are given a cohesionless soil. That means failure envelope will start from this, or the Mohr circle, it will touch like this. It will the failure envelope will start from 0. Okay. So what happens here is, this is phi. We have to find sin phi. Sin of phi. Sin of phi, what will be equal to? Sin is perpendicular by hypotenuse. Perpendicular is this, hypotenuse is this. So this will be equal to this portion. Hypotenuse will be sigma 1. This is sigma 1. This is sigma 3. Sigma 1 plus sigma 3 by 2. Okay. This portion perpendicular will be sigma 1 minus sigma 3 by 2. Why? Because this is the radius. Okay. This will be sigma 1 minus sigma 3 divided by 2. So from that we know this equation is sin phi is equal to sigma 1 minus sigma 3 by 2 divided by sigma 1 plus sigma 3 by 2. Note this is only for cohesionless soil. Okay. If we have any cohesion intercept here, so the equation will change and this is not applicable, right? Phi is given as 30 degree. Okay, sin phi is equal to sin 30 is equal to sigma 1 minus sigma 3. We are given confining pressure here. Confining pressure is given as 200 kilonewton per meter square. So sigma 1 minus sigma 3, 2 will go. Sigma 1 minus 200 divided by sigma 1 plus 200. So sin 30 is 0.5. 0.5 multiplied by sigma 1 plus 200 is equal to sigma 1 minus 200. So 0.5 sigma 1 plus 100 is equal to sigma 1 minus 200. 0.5 sigma 1 is equal to 300. Sigma 1 comes out to be 600 kilonewton per meter square. Calculating the deviator stress at failure, sigma d is equal to sigma 1 minus sigma 3. Sigma 1 we have calculated, sigma 3 was given. So difference between them, that gives the deviator stress equal to 400 kilonewton per meter square. Okay. Let's move on to another question. That is question number 9. Question number 7. The following results were obtained in the shear box test. Determine C and 5 parameters. Normal stress in the test 1 was 1 and the test 2 was 2. Shear stress was in test 1 1.3 and in test 2 1.85. So here the shear box test is used and we have to determine C and 5 parameters. This is the shear test. This is the question on shear direct shear test, that is DST. We know that the shear strength is equal to C plus sigma tan phi Mohr column theory. So here let me explain what shear strength. Shear strength is simply the shear stress that we have at the failure, that is called as the shear strength. Okay, here two tests, we minimum of 2 tests are required to get the envelope, to get the failure envelope. This is a straight line, we at least need 2 points to join this. Okay, if we have 3, that means it is more accurate. Minimum of 2 tests are required to get the failure envelope or to get the C and phi. Okay, what is phi? Phi is the slope of this line, failure envelope. Test 1, for test 1 1.3, tau f is given as 1.3, it was calculated. It is equal to C plus sigma tan phi. Sigma is 1, tan phi. This is equation 1. For test 2, 1.85, tau f is 1.85, C we have to calculate. Sigma is given as 2, tan phi we have to calculate. So we are given here two equations, 1 and 2. So if we solve these two equations, we can solve, you can solve by any method, substitution method or elimination. From that we can get phi is equal to 28.81 degrees and C is equal to 0.75 kg per centimeter square. Note that here the what are the units here. Phi is simply, it is an angle. Okay, it can have degrees or radians. Normally it is termed in degrees. Okay, C here, please note this important, C has the unit of stress. Okay, kg per centimeter square, or you can write as kilonewton per meter square. It has the unit of stress. Okay, that is C. So this completes this question. This was a simple question, no much to find. Also I would like to explain a few things here. So we know C is the cohesion intercept and phi is the angle of internal friction. If we have a soil, right, we have a soil, it doesn't have a constant C or phi. Okay, this C and phi depends upon the type of test we are doing and the drainage conditions in those tests. Okay, suppose you have a soil, you calculate C and phi by any drainage system. By keeping the drainage open, you find a C and phi, and then the similar sample, same sample, but with the drainage open, but with the drainage closed. Here this was drainage open drainage, now it is drainage closed. It will have different C and phi, right? It depends upon how what type of test we are doing and what are the drainage conditions here, whether it is drained or whether it is undrained. Okay, it doesn't have a constant, it's not a constant value for a particular soil. Okay, this is very important to know. So let's move on to the last question. So the last question, it is a little bit lengthy question. Let me read the question first. The following test results at failure conditions are obtained from consolidated triaxial tests on samples from a saturated clay strata. Note that here what we are given consolidated triaxial tests on clay. Specimen 1, confining stress is equal to 2.75, deviator stress is equal to 1.5, pore water pressure is equal to 1.5. Specimen 2, sigma 3 is equal to 4.25, sigma d is equal to 2.2, pore water pressure is equal to 2. We have to find the shear strength parameters, that is C and phi. Okay. So what we are given, this is in the form of table. We have to find Cu, phi u and C dash phi dash. As I said, this Cu and phi u means when we are doing the undrained test. This undrained. C dash and phi dash we get when we are doing the drain test. Okay. When it is drained, C dash and phi dash. When it is undrained, Cu and phi u. You can remember by noting this. It is Cu. U means undrained. Phi u here u means undrained. Okay. In terms of total stress, this is another equation, very important equation. Sigma 1 is equal to sigma 3 n phi plus twice Cu root of n phi. Okay, here n phi is the flow ratio. It is equal to tan square 45 plus phi by phi u by 2. This is important equation. You will be using this more often when you are calculating or you are dealing with the shear strength of the soil. Sigma 1 is equal to sigma 3 n phi plus twice C root of n phi. Okay, why here Cu? Because we are doing in terms of total stress. So sigma 1 is equal to sigma 3 tan square 45 plus phi u by 2 plus cu tan 45 plus phi u by 2. For test 1, sigma 3 is equal to 2.75. Sigma 1 we can calculate by sigma 3 plus sigma d. It comes out to be 4.25. So here 4.25 is equal to 2.75 tan square 45 plus phi u by 2 plus twice cu tan 45 plus phi u by 2. Okay. In test 2, 6.45, that is the sigma 1, it is equal to 4.25 sigma 3, that is sigma 3 tan square 45 plus phi u by 2 plus twice cu tan 45 plus phi u by 2. Okay, so by solving these two equations we can find the phi and c. Now we'll see how we can calculate that, because this is very simple. These equations are simple equations. Your the only variable here is the phi. Okay, we can simply calculate that. Variables are 2 in number, that's why equations are 2, phi and cu. You can calculate easily from the calculator. You please watch some videos how can we calculate that. So here the phi u comes out to be 10.9 and cu is 0.089 kg per centimeter square. Now this was it was in terms of total stress. Now we have in terms of effective stress. What happens is sigma 1 dash is equal to sigma 3 dash tan square 45 plus phi dash by 2 plus twice c dash tan 45 plus phi dash by 2. Here phi dash and c dash are used, right, when we are dealing with the effective stress. So sigma 3, as it is effective, so we will be using effective stress, that is sigma 3 dash is equal to sigma 3 minus u 2.75 minus 1.5, it is 1.25. Sigma 1 dash is equal to sigma 1 minus u, it is 4.25 minus 1.5, it is 2.75. Substituting in effective stress equation, 2.75 is equal to 1.25 tan square 45 plus phi dash by 2 plus twice c dash tan 45 plus phi dash by 2. That is the equation 1. 4.45 is equal to 2.25 tan square 45 plus phi dash by 2 plus twice c dash tan 45 plus phi dash by 2. It gives the equation 2. So when we solve these two equations, what happens is we get phi dash and c dash. Okay, here are two equations are given and there are two variables. We can solve that easily. So that was the last question in this lecture. Okay. So in the end, I would like to show you some practical examples, of the shear test. Okay. So this here is the graph. This is the direct shear test. The how what we get in the laboratory. Okay, so like here in DST normal stresses, we are given normal stresses, we have normal stresses, we have shear stresses, we calculate them, and then we plot the graph between these two to get the failure envelope. Here you can see we have 3 points are given here, so we can produce a line that is more fitting. Okay, and then in the code you can do that. So from that we can find this failure envelope, and then we can find C and phi. This is the practically the student has done. These are the results here. Okay, the C came out to be 6.38 kilopascal and phi came out to be 11. This is the DST. So here putting the graph, you can see we have the shear stress versus strain. You can calculate that and then plot the graph between the two. The plot comes out to be like this for one normal stress 0.5, for normal stress 1, and for normal stress 1.5 kg per centimeter square, and this came out to be like this. And then we can calculate the shear stress maximum for each, and then putting them here and then getting the graph. Okay, and then finding C and phi. This is the DST test. Okay, so that will be all, I guess, for today's lecture. I hope you have seen the videos, and these questions here will definitely help you in getting through the examples, whether when you actually perform it in the laboratory, what is happening there, and if you have any questions, numerical questions, you can easily calculate. Okay, so that will be all. Okay, we will meet in the next week. Okay, bye.